Hello friends, let us talk on Fermat's little theorem. The statement is, in number theory, Fermat's little theorem states that if p is a prime number, then for any integer a, the number a to the power p minus a is an integer multiple of p, or it is divisible by p. In the notation of modular arithmetic, this is expressed as a to the power p is equivalent to a mod p. For example, if a is equal to 2 and p is equal to 7, then 2 to the power 7 equal to 128 and 128 minus 2 equal to 126, which is 7 times 18. So 126 is divisible by 7. If a is co-prime to p, then Fermat's little theorem is equivalent to the statement that a to the power p minus 1 is an integer multiple of p. Or in symbols, a to the power p minus 1 is equivalent to 1 mod p. For example, if a is equal to 2, p is equal to 7, then 2 to the power p minus 1, 6 equal to 64, and 64 minus 1 equal to 63, which is 7 times 9. So this is Fermat's little theorem, and this came to me while I was trying to solve a problem, a math Olympiad problem. Find the prime number p between 2000 and 2075 that divides 2 to the power 10 factorial minus 1. So it's impossible to calculate manually. 2 to the power 10 factorial minus 1 is divisible by a prime between 2000 and 2075 or not. But if we apply Fermat's little theorem, I got a sketch of a proof that it gives a solution. Primes between 2000 and 2005 or 2003, 2011, 2017, 2027, 2029, 2039, 2053, 2063, 2069 and 2071. This I got by a simple program in Python. From Fermat's little theorem, 2 power p minus 1 is equivalent to 1 mod p, because p is a prime, so 2 is co-prime to p. There is no common factor between 2 and p. So we can say from Fermat's little theorem, 2 power p minus 1 is equivalent to 1 mod p. Now we need the concept of order of 2 modulo p, which is written as odd p of 2, is the smallest positive integer d, such that 2 to the power d is equivalent to 1 mod p. So odd p2 is divisible by p minus 1. This is not clear to me. I got this solution from ChatGPT. I gave the problem asking it not to use computer and give a mathematical proof, and ChatGPT outlined this problem to me, but this is not clear to me why. We know 2 to the power p minus 1 is equal to 1 mod p, and 2 to the power 10 factorial minus 1, and 2 to the power odd p2 is 1 modulo p, so it is saying that odd p2 is divisible by p minus 1, but this is not clear to me. So to check a prime number p divided 2 to the power 10 factorial minus 1, it is enough to check whether odd p is divisible or odd p divides 10 factorial or not. Let us check for 2 to the power for p equal to 2 to the power 2 to the power 39, which is a prime number between 2008 and 2007. How we arrive at 2039 is not clear to me, and to 2039 minus 1 equal to 2038, which is 2 times 1019. The possible orders of 2 mod 20239 are divisors of 2038, which are 1, 2 and 1019. This is the factorization of 2038. Now 10 factorial equal to 36288800, and 2 to the power 38 divides 10 factorial. So 2 to the power 39, which divides 2 to the power 10 factorial minus 1. So that is the answer, and I got this answer from ChatGPT. ChatGPT gave a length of context, which is the proof of the theorem. Let us see into it. I gave the problem, find the number between 2000 and 2075 that divides 2 power 10 factorial minus 1 without using computer. and it starts with e to the power with Fermat's little theorem. E to the power n minus 1 is divisible by primes p such that order of a modulo p divides n. So the proof goes next. It relates Fermat's little theorem with orders. Then it starts with 2039, a heuristic search between among the primes between 2000 and 2025, and finally some heuristic arguments which could be settled if one calculates carefully. It comes up with the answer 2039. Let me tell you, I did a simple calculation of this fact that 2038 divides 10 factorial or not, which I found false, but still ChatGPT uses this argument. The proof is not clear to me, but this is the way ChatGPT is generating mathematical solutions without using computer. So I'd stop here. Like, comment, share, subscribe my video. I am available for one-to-one sessions too. Thank you.